My name is Rafael. I'm from the Econ department, and I'm one of the coordinators here of the colloquium. And today I have the pleasure to have Professor Marcelo Medeiros from University of Illinois. He's a professor in economics and also the Lehman Endowment Chair at the University of Illinois Urbana-Champaign. He has a BA, Master's, and a PhD degree in electrical engineering from PUC-Rio in Brazil. And over the years, his research agenda pretty much evolved from nonlinear time series models to high dimensional time series and machine learning. Okay, and I actually have one of my favorite papers that was published by him that I use in my course to tell the students the money in banking and time series econometrics, which was the one on inflation. So I gotta get the title here. Forecast inflation with a data-rich environment, which was published in 2021. Yeah, I love to show that as an example of machine learning being applied to time series in class. He has over 50 published papers over his career, and some of those papers were actually published in top statistical econometrics journal like JASA, the Journal of Econometrics, and International Journal of Forecasting. And he's a fellow of the Society of Financial Econometrics, and he's also associate editor for JASA, for the Journal of Business and Economic Statistics, and for the Journal of Financial Econometrics. And today, he's presenting his paper, Balancing Flexibility and Interpretability, a Conditional Linear Estimation via Randall Forest. And I, as understood from the abstract, I think you're trying to build this bridge between model prediction and model interpretation, which is actually quite useful for those who work with applied statistics. For example, in my case, in finance or economics or even other fields. All right. So thank you very much, Marcelo, for coming, and the floor is yours.
Okay, so thank you. Thank you for the nice introduction. It's a pleasure to be here. First time in Boise and first time in Idaho. This is a joint work with Ricardo Mazzini, a long-term co-author who is at the stats department at UC Davis. And as Rafael said, the idea here is to balance the flexibility of machine learning methods, but also with some interpretability. That's something that we like in economics. So this is the roadmap. And so just to give some context, there's this boom in machine learning models, not only in economics, but also related areas. And you can think about like this debate between like when you have a fully parametric model, so you want to basically explain the behavior of some variable given a set of other variables. And usually when you go like to standard stats, and econometrics classes, you try to figure out a model, let's call it G, and it can be nonlinear, but you have a lot of restrictive assumptions about G, and this function is indexed by some parameter theta. So you may say, well, the relation between y and x is linear, or the relation between y and x is polynomial, right? But you like really restrict the functional form, but the idea here that, well, when you restrict it, it's not that flexible, but you can tell a story about the model, right? And you can tell reasons why you pick this specific model. On the other extreme of the spectrum, we have the non-parametric machine learning, fully machine learning methods would say, I don't know what this function is. There is a mapping between x and y. I have no idea what it is, but I have here a set of, let's say, black box tools, right, that can try to approximate this function, okay? And so we leave it very general. So usually we just impose some very weak conditions on the behavior of f, and you let the data speak, okay? However, in most of the cases, of course, you may have way better predictive ability than a restricted model, because the model can adapt to new data sets more easily, right? But you lose interpretability. sometimes very difficult to tell a story of what's going on here. So this paper that Rafael mentioned that I wrote on inflation forecasting, one of the big debates with the referee said, oh, hey, you have this fantastic machine learning here, methods, they are providing forecasts that are way superior than the benchmarks, but why? Why these models are performing better? What are the mechanisms? What we can tell, for instance, central bankers, why central bankers, policymakers should use your model? What's the story behind? And then we had a really hard time to come up with a story. And I don't think that we fully addressed the question, okay? So the idea is trying to find something in between here, okay? Go between these two here. And also, usually the question in economics that we want to know is what's the impact that X has on Y? Okay? What's the impact of monetary policy of on inflation, right? Or if you do like in epidemiology, what are the impacts of vaccinations or lockdowns on the spread of a disease, right? So you want to measure impact. So usually the quantity of interest is not the function F itself, but you want to say something about how F changes as X changes, right? You want the derivative, okay? Or you may take this derivative, the expected effect over some other variables Z. So you want the average partial effect, okay? And it happens that if you have this fully flexible model, it's kind of a challenge, okay? In terms of statistical guarantees to come up with an estimator of function F, okay? So it's far from trivial moving from F to the derivative of F with respect to X, okay? So the question is, can we try to solve this problem, right? And so what we are going to do is to complicate the model in one dimension, but in order to simplify in other dimensions, right? So instead of writing a function that's super general, y as a general function of two set of vectors, right? So imagine that this is the variable of interest, right? We want to measure the effects. Basically, what we want in the end of the day is to see how this changes, this partial effect. But you may have other variables here, okay? What we're going to write is the following. I'm going to say that what we have is a local linear model, okay? So, in fact, given a variable Z, the impact of X on Y is linear, but this impact is heterogeneous. You have heterogeneity, and the sources of heterogeneity is the Z, okay? And we expect, because it's usually the case, that these vectors, this variable X is of low dimension. Usually we're interested to see the impact of one or two variables on Y, but not many, right? But on the other hand, if we fix the model to be linear, well, that's the simplest thing we can do. Of course, we lose all the flexibility and all the nice things that we have been learning from machine learning developments, right? So we want to make the linear model kind of flexible by allowing the linear model to be just in a local region, right? And so we have this heterogeneous effect here. The good thing is, if we estimate the model, we not only have a predictive model that's going to be given by X prime beta Z, so X prime here means transpose, but this is a vector, but also it gives us the partial effect of interest automatically. It's beta Z. So we have on the same estimation, we don't need to change anything, both the prediction, but also the component that we are interested if we want to give some interpretability. We have the partial effects. Okay? You may think, but don't we want the partial effects with respect to Z? Well, in most cases, no. Well, this can be like a treatment, an intervention, a different policy, right? And so that's what you want. Of course, if you want the impacts of Z, yeah, then we're not gaining anything. We go back to square root 1, right? But if we want the impact of X, right, then this is a very nice model. Okay, so that's the idea. And this type of model is not new. So it dates back from the 70s, at least, right? But we are going to take a fresh look at them, right? So we're going to look at these models from a modern machine learning perspective by allowing flexible estimation of beta Z, and also when Z can be several variables. We don't need only one. So you may think about what's of the impact of education on wages, but the impact depends on several characteristics of the individuals, right? Where the individual lives, the parent's background, gender, race, so on and so forth.
Quick question, and Z may contain X?
Z may contain X, okay? Z may contain X, but usually if Z contain X, it could be a little bit more complicated, because then we have to take the derivative of beta with respect to X. So in most of the applications, we're going to think that this can be correlated,
Okay.
but to get the full interpretation, the Z must not contain X. Or at least the elements of X that you are interested in the partial effect. Okay? Okay, so that's basically what we do. So how we are going to recover beta? Well, random forests. Okay? And we're going to try to motivate why random forest. So to make put into perspective of previous models, just to show you, okay, this kind of idea is not new, right? If we go back to the 70s in statistics, there was this model called switching regressions. So it's basically that you have two linear models, right? But two different regimes. So you may think, wow, you have one model when the economy is going up, another model when the economy is going down, right? And you estimate models like that. But the thing is that here is a sharp distinction in between the two regimes. It's only two regimes, and usually what drives the changes, the switching, is only one variable. You have only one cause for the switching, okay? And then we can generalize this to multiple regimes. So there's a bunch of literature in the 70s and in the 80s about that, okay? Later on in my own research, in my very early days, we tried to generalize this switching by allowing kind of a smooth transition between those linear models, right? But again, the whole cause variable here was a scalar, right? And these functions f were kind of restricted to some very specific class. And of course, also there was these varying coefficient models, right? Where you estimate this fully non-parametric, but again, this z was a scalar. So this was all before the machine learning boom, okay? So you can look at these as like classical development, classical papers using the standard statistical methods available at the time, okay? All right, so here we are going to make this more general, right? So we're going to use these varying coefficient models meeting a random forest, right? And let me give you some examples, right? I'm going to give you, for reasons of my own preferences, be examples in economics, but I will try to give like other applications as well. But one typical thing that came to my mind is in economics, we have this Phillips curve model, right? Which basically from macroeconomics, it explains what are the determinants of inflation. Okay, what makes inflation changes over months, right? So usually in the literature, this is a linear model saying inflation today depends on inflation in the previous period, because prices do not change like crazy, right? So you have like some stability. The other term is expectations, how individuals, agents think inflation would be, right? Because if you think, oh, inflation will go up, right? And I'm a retailer, I'm go there, I'm going to change my prices. Okay, so expectations, what you expect, also influences the model. And another measure of economic growth, like the GDP growth, for instance, right? And these models were linear, but there's a bunch of evidence saying that, well, these reactions here, how inflation reacts to past inflation, how inflation dynamics reacts to expectations, or how inflation dynamics reacts to the state of the economy, changes from time to time. Okay? And usually it's related to periods where you have more uncertainty and periods that you have less uncertainty of what's going on with the economy, right? So economic uncertainty, political uncertainty, all these things, right, affect the dynamics of prices. So if you have a period of high instability, right, we see prices going up. So we experienced this in the US aftermath of COVID, because there's a huge uncertainty due to the COVID, right? Disruptions in the supply chain, right? So supply of products went down, demand went up, so prices were changing. So these coefficients here may change, but we don't know how, right? We don't know what are the drivers. So there are many factors that may change. So we don't know. So we can do it in a flexible way. And our machine learning can help us, right? If we write this model this way, we can throw here a bunch of things that may be drivers for inflation dynamics, right? And we're going to let the data tell us how those coefficients will change. So it will give us the heterogeneity of the coefficients. Our specification can deal with this case. Okay, this is one specific example. Okay, another specific example is that, well, we are going to construct some treatment, a job training program, for instance, or you want to give incentives to students, right? Some students will get some extra credit, some other students won't get extra credit, right? And you want to know what's going to be the final performance of the student, right? Well, but not all the students react the same way to incentives, right? So there may be several characteristics of the students that will make the effect of the treatment different, okay? So this is a typical model. So imagine this is performance. This is which kind of incentive we are giving to the students. And this is the effect that we want to measure, but this effect is not fixed. It's not that all the students will have on average the same effect. This effect may depend on characteristics of the student. Okay? So past courses, age, background, several things that may enter here, and you want to know, right? If you want to design a policy, you want to know how different students react to that policy. So if you have a group where you have an effect much larger than the other one, you may focus your attention to this specific group, because it's where you're going to see like the bigger benefits. And the groups that do not react a lot, you don't need to give any incentive. So you want to capture this heterogeneity. Okay, so this is an example of heterogeneous treatment effect. So you can think about this in client, if you're a big tech and you want to expose different customers to different types of ads, right? But how clients react to ads depends on their characteristics. Okay, so this is another example. of our model. We can also think about a linear model where you have just some kind of fixed heterogeneity here. So your interest relies on estimating this coefficient. It's fixed, but there's some grouping effect, right? Like spatial grouping and things like that. You may use this approach. So this setup of locally linear models encompasses several other methods, right? That can be applied not only in economics, but in several other situations, okay? So the question is, okay, Marcelo, but why you're doing random forests? Why not deep learning, right? Why not any other tool? Like, why not boosting, right? Why not boosted trees? Why not support vector machines, right? There are so many in the toolbox. Well, I think the cynical answer is because we have to pick one, right? But there are some reasons, both from the practical point of view and from the theoretical point of view, right? From the practical point of view, is easy implementation, okay? Very efficient algorithms with few hyperparameters to tune, okay? And super fast algorithms, right? That are less prone to cherry picking. If you think about, I don't know how many of you ever tried to estimate a deep learning model, a deep neural network. You have many things to select. How deep is the network, right? The number of neurons in each hidden layer, the type of training algorithm, right? The type of regularization. There are ways, so many things, right? Then that's almost impossible, for instance, to replicate results. And it's very computer intensive, right? So that's the second reason. The third reason is that we can handle categorical missing data from a practical perspective. Well, from a theoretical perspective, this is a challenge. But if you don't care about the theory, you just care about being able to apply this model, you can have missing data and categorical variable very, very easy, okay? From the theoretical point of view, that interests me the most, right, is way less difficult. It's still very difficult, but it's less difficult to analyze from a theoretical perspective than deep learning alternatives. What do I mean by theoretical perspective? Are we able to say something about the estimated model if there is a true function, the true heterogeneity, right, that relates y and x? Am I able to recover this true relation as the number of observations grow? And the answer is that with random forest, we can show that's possible, right? And it's feasible to analyze in high dimensions, although the results I'm going to briefly show here today is for low dimension stuff, but it's possible to generalize this to high dimensions, okay? So these are the reasons why we pick random forest, okay? So let me give you the setup, okay? So our goal is to explain why, and this is a scalar. This is one variable. We have a vector or variables of interest that has dimension d of x. So it can be one treatment, multiple treatments, can be different variables. And z is like the covariates that causes the heterogeneity, the sources of heterogeneity in defects, right? And basically we are postulating that what x beta z means is the condition expectation. Okay, so it's the best predictor in mean squared error sense. Okay, so we want the best approximation, and we want to learn this and the derivatives of the conditional mean. Okay, how a tree works is basically we imagine that we have a space here of two variables, z1 and z2. So the idea of a tree is to start splitting this space like in different regions, right? And estimating local models in each region, okay? A usual tree is going to put like the local model will be just a simple average. Okay. In our case, the local model will be a linear model. Right? So, and how we decide the splits is a greedy algorithm, right? We want to always to find the best split in terms of minimizing the sum of the squared errors of the mean squared error. Okay, and we keep growing the tree, keeps dividing the space until we get to a very small region here with a minimum number of points, and then when we stop. So we are going to cut this space, we're going to slice this space as in several different small rectangles, right? And we want a minimum number of points there in order to estimate our local model. Okay, so that's the intuition. Okay. So, however, and if we want to prove some results, we have to change a little bit the algorithm. So what we are going to do? First, we are going to work with random forest. We are not going to estimate a single tree. We are going to estimate multiple trees. Okay? And then we are going to combine them. So how we are going to do this? So imagine that we have a sample of endpoints, my blue circles. Okay? I'm going to take a subsample of size s less than n. This is the approach for one single tree. I'm going to repeat this 1,000 times, 5,000 times, okay? So I'm going to create a subsample. So I'm going to randomly pick from the original row of blue circles, a second row of blue circles where I'm going to just take s less or equal than n, okay? So it's going to be a subsample. It's very important to be a subsample. Then what I'm going to do, I'm going to divide this subsample in two different groups, the greens and the pinks, okay? And be approximately half-half. This is a very important point, okay? And then what I'm going to do, I'm going to take the pink and I'm going to use the pink points to split the sample, to slice my space of variables. So I'm going to grow the tree, okay, using only the pink sample. And I'm going to use the green points to estimate the local models. So once we slice that, we discard the pink points and we estimate the local models with the green points. You're going to say, but why is that? And this is a major difference from the original plain vanilla tree growing process. This is what we call an honest tree. The thing is that when we want to estimate this function, beta z, right? Remember, we are saying that y is equal x beta z plus u, right? We want, for instance, to test some hypotheses on beta z. Is beta z constant? Is beta z a square function? Is beta z constant within some values of z? We may want to ask questions about that. So we want to conduct a hypothesis test. To conduct a hypothesis test, we need to know what's the distribution of our estimator, beta hat, okay? And ideally, we want this estimator to behave like a normal random variable, a Gaussian random variable, okay? The only way we can make a tree, like the tree estimation, to be Gaussian is with this procedure of having the pinks and the greens. We have to split the sample. We have to use one part of the sample to grow the tree, to slice my region, of the covariates and use the green dots, the green sample, to to estimate the linear models. Otherwise, the estimator won't be normal. And if it's not normal, then no hope to conduct any inference. So that's the first change that we have to make. Okay. Yeah.
But why the first step of selecting a subsample? Why
Because we're going
choose-
to repeat this 1,000 times to reduce variance. Okay, so this is one tree.
Yeah.
And now we are going to repeat this procedure 1,000 times and you'll take the average.
Okay.
Okay?
So when splitting the subsample into two different groups, it's like randomly choosing, again randomly choosing those two groups, or
Now you don't need to randomly pick. You can just divide on half. The first as divided by 2 and the last as divided by 2. You don't need to randomize at all. They just need to be different. Okay? Okay, so that's what we are going to do. So we are going to call the greens and pinks A and A complement. Okay? And then we run everything, and we run this for every tree. We estimate every tree, and every tree has a degree of randomness that we call omega, because every tree will be estimated on a different subsample. And then our final estimator will be the average of the estimated betas on each tree. Okay? And what we have to show is that we want the variance term to go to 0, and we want the bias term to go to 0. A lot of technicalities here. I'm going to skip the technicalities, right? But this is easy to work with. This is a huge nightmare. This is what causes the bias is the problem. Okay? One thing that's important is that when you probably see this when you work with whoever worked with random forests or trees, that you had to decide on the minimum points that you have in each region. Okay? And usually we say that we fix as a value of K. And we keep this fixed. Oh, it's going to have like 3 points, 5 points, 10 points. Okay. Unfortunately, because we have these two samples, this is tricky because the K, right, is related to the pink sample because that's where you're growing. But you have to enforce that when you pick the green sample, you also have points in the regions, because otherwise you cannot estimate anything. So if you make this K very small, there's a probability that tends to 1 of having no points when you pick the green sample. So you cannot estimate the local model. So we had to construct a whole new theory. So basically, this value of K here, the number of points, has to diverge with the sample size. The larger is your sample, the larger must be the number of points that you have here. Okay? And another thing that's important is that when you split, so this is all technicality, let me skip this. Let me show you something that's, no, it's not here. Let's go back here. Another thing that's important is what we call alpha regularity. What alpha regularity means? You are here, you have your tree, right? So you are in this region here, okay? Let's say that you made the first split, so you are here, okay? And you are on this side of the tree, and you want to know, should I put a decision here. So should I split this region again? Okay. We must guarantee that on both sides, okay, we are going to have a fraction alpha of the points that we have here. Okay. What's the intuition behind that? Imagine that these are the points in this region, okay? We don't want to put a split here. Or even worse, we don't want to put a split here, because this split means nothing, okay? What happens that the recent paper by folks at Princeton, they show that if you're doing a tree and you have irrelevant variables, right? Or you don't need to split anymore, but you need to guarantee a minimum of points. What the original CAR algorithm from the tree literature, the algorithm will put the split on the boundaries, on the extremes, either here on the top or either here on the bottom. And what's going to happen is that your estimates will be completely screwed. It's going to be completely wrong. Okay, and no hope of trusting your estimates. Whenever you say that you need a fraction of the total observation on both sides, okay, then you guarantee your result. So basically what we need a fraction alpha that is between 0 and 1 and half, sorry. Okay. And you need a number of points to be between k and 2k minus 1. So you need to satisfy these two conditions. And this k diverges as n diverges. So if you have this, and this is all implemented in the algorithm, then everything works. And I have only 10 minutes. I'm going to skip all of this, just show you the following. These ugly formulas is basically saying that you can trust our estimate. So our estimator will converge to the true function under mild conditions, right? And the rate of convergence will depend on a bunch of things, right? The LP norm will also converge, so you can look at the variance of this thing, and any moment of this thing will also converge. And more importantly, we are going to show that the tree also converge to a normal random variable. So we basically have this result here on the top. Our random forest converge to estimator converge to a normal random variable, so we can do inference. Okay, of course there's all these technicalities here of a bunch of crazy formulas. You have to estimate the variance, but we have algorithms to do all of this, I promise. Okay, so let me show you just a numerical exercise for you see how good or how bad is our model. So I simulated 2 TGPs. Okay, and the first one, the heterogeneity is given by like 3 factors, right? It's a bunch of indicator functions. So function I is going to be 1 if this condition is satisfied, 0 otherwise, and all the variables are normal. In fact, this type of function violates one of our assumptions because we need data to be Lipschitz continuous, and this is not, it's a continuous function, but we want to know, well, how the method behaves. And the second one is a continuous function, this nonlinear approach, okay? So what I'm going to do, I'm going to simulate this data with different number of observations. We are going to estimate the model, we are going to repeat this many, many times, and I want to know on average what's happening, okay? So I'm going to repeat this 500 times, We have the number of subsamples will be 80% of the total number of observations. We are going to work with 100, 250, 500, 750, and 1,000 observations. And we are going to make px, the dimension of x1, the dimension of z is n divided by 4. And that's basically what we have. First, one thing that's important, in all these models, the standard deviation of the unknown error is 1. So if our model is doing a good job, we hope to have an estimated residual that has standard deviation equal to 1. Okay? And what we have here is that, well, the residual average is almost 0, so really we are estimating something that's not on average good. But look at the residual standard deviation. As we increase the sample size, these things are going down. So really the model is becoming more and more efficient. The only thing that happens is that we have a bit of overfit with 1,000. This is due to the fact that the function is not Lipschitz. So we have some overfitting. But you see that the standard deviation of the estimation error of the function is going down as expected, showing consistency, right? And if we look at kurtosis and skewness, they are converging to the kurtosis and skewness of a normal random variable. Okay? And if we look at the distribution of average partial effects, so the average of beta z, we have something that looks like Gaussian, like corroborating our theory. Okay? If we go to the second data generating process, we have the same thing. Residual average is 0. Residual standard deviation is converging to 1. And here there's no overfitting, but because the function in this case is a Lipschitz continuous. And the same thing, the standard deviation of the estimation error of the betas is going down. Kurtosis and skewness going to 3 and 0, what's expected. And when we look at the average partial effects, again, something that looks like a normal distribution, okay? Even when the sample is pretty small, which is kind of nice. So corroborating our theory. So yeah, so that's our conclusion. So we'd like to bridge interpretability and with flexibility, right? We prove consistency and symptotic normality, okay? And as some challenges, we can do inference on whenever we set z equal to lowercase z. So we can do inference on this object, using this object here, okay? But if we want like to do an inference that's uniform over the whole function, this is still a challenge. We are working on that. We are now working on generalizing also the results for high dimensions, right? When the dimension of the variables is larger than the sample size. And also all the results I show you is for IID data. We are now generalizing it for time series data. So that's it. Thank you. I think
Questions?
Where can I find the recording for this?
Talk about that later.
Okay.
yeah.
Can you go back to the page 14?
14, yes.
Yeah. So I said, oh, in your simulation, you also just considered a vector of variable interest in the x. Could you also add 1? So you have like 2 parts, so x part, and I mean the beta z and then x transpose the.
Yes. Yeah. This x here can contain an intercept.
Okay.
So we can have both, and we can have additionally something here that like these things here. And we can have something that the model that's not changing. So we can have once you have like the umbrella model, all these subcases are almost automatically handled.
And I also, sorry, I also kind of have a question. Could you see, I kind of missed the part, your beta hat G is the average of all.
I see.
Over R.
We have
Oh, okay.
beta hat is for one single tree.
Okay.
Okay. So, and then we have the forest,
Mhm.
which is the average over the trees. The way we show the results, we show that each tree is consistent. Okay. And then when the average is important to make the variance to reduce and to attain the asymptotic normality. Okay.
Thank you.
And then this is the bar.
I thought that all your decisions for picking random forests over other machine learning classifiers were good, but I was wondering, did you ever consider like from preliminary testing like other models or do prior works kind of compare different ones?
Okay, so that's a very good question. My PhD dissertation 25 years ago was exactly this model with a neural network, a shallow neural network, right? That was much simpler than estimating the deep learning model. And when I started this but at that time, the dimension of Z should be very, very restrictive, right? We didn't know how to estimate things with large Z. So when we started this project, we thought about, well, let's make my PhD dissertation alive again, and let's take exactly that model. And then we start playing around. The performance was horrible, if the Z was too hard, right? In terms of computing time and selecting the architecture. So I didn't try, to be honest, I tried one or two, like with more than one layer, but it was not working. It was not something that we can like just put the defaults and move on, right? On the other hand, with the random forest, with only few things to, of course, there are some key things that we have to decide. It was basically the alpha and K, but you can make these arbitrarily small and things will work. So that was the reason. And then when we thought, okay, it's working, then we started doing the theory.
I have a question.
Yeah.
So the reason why I asked in the beginning if Z could be equal to X or if Z contain X, because it seems to me that if you just replace Z by X, you're gonna go back to some sort of like adaptive kernel model, which you have like the bandwidth essentially vary according to your random forest.
Yeah. If you have a model that's like this, okay, if you have like this, then there's no point in making the
No, it's the point because you can estimate a kernel regression.
yeah, but then we can just call this G of X and estimate a pure random forest.
I see.
You don't need the interaction terms,
I see.
right?
I see.
So the benefit of that saying, okay, you really, again, if your focus is just, I want to make predictions, just don't even bother reading my paper, right? Keep the original random forest, deep learning, or your favorite machine learning method. Here is when you want to make interpretation and you have some kind of particular model in your mind. You have an X that's low dimension, in most cases a scalar, which is a treatment. And you believe there is heterogeneity, and heterogeneity is given by other variables than X, not by the treatment itself, but they can be correlated. So the Z that you put here can be correlated with X, can be highly correlated with X, but not exactly X. Because the idea is that when you take the derivative of Y with respect to X, you get the betas. You don't need to take the derivative of the beta. Because if you have an X inside the beta, then you go back to the original problem, right? Then you have to take the derivative of beta, and that's exactly what we want to avoid.
So I was thinking, because there are those asset pricing models, they are all linear, like 5-factor model, 3-factor model. And most of those models, they do this smoothing of beta to try to basically forecast what will happen, what will be the returns in the future. So I was wondering if you can actually apply exactly that case. You have a 5-factor model, you interest in the beta of each factor.
Yeah, so imagine here,
but then you make
you have returns and you have the beta here of something.
Yeah.
And here you have the factor, right?
Yeah. And then I was wondering if the beta.
You can, because the factor is aggregated.
No, but I was wondering if the beta, you can actually make the beta vary with other factors. Like you have factor 1, the beta for factor 1, and then you have the beta for factor 2, 3, and 4.
This thing here.
And it kind of improves the model.
You can do something like that.
Yeah. And it kind of is an improvement what we do right now, because what we do right now is just like this, do this smoothing of data.
The only problem, because then, no, you can't, right? Because if you look, if it's a forecasting problem, then okay. But if at the moment you want to do this,
I see.
This will be beta F2. That's cool, no problem.
Yeah.
But this will be F2, derivative of beta F1 with respect to F1.
Yeah.
And this is the whole thing that we want to avoid.
I see.
That's taking the derivative of this machine learning. Although you have results, we have results like the original universal approximation theorems for neural networks that you can approximate the derivative. But that's like in terms of function approximation, and it goes to statistic. But can you estimate this thing that approximates both things at the same time? Can you do inference on this quantity here? Then the answer, we don't know. There are no results whatsoever in the stats literature about that. So the idea is that, well, that's why I said we are going to make it more complicated in one dimension, but we are simplifying dramatically in another dimension. And that's what the price you have to pay, right? There's no free lunch, right?
So, I mean, in a different lifetime, I did a little bit of an observed heterogeneity in B. Would you be able to pair that with here? So suppose that one of the Z's is, I mean, you have a missing signal. So there is a distribution, unconditional distribution over those.
Yeah, it's not immediate. I think we would be able to do it. I don't know how complicated it would be.
Okay.
It depends on what you want to show theoretically. Right? With an IV procedure, you probably can.
Okay.
He had a question.
Thanks for the nice presentation. So I think you have mentioned like the application in the context of your random forest and the generic one. So I wanted to know, like, have you ever compared the computational time for your one comparing the generic random forest?
Yes. Although it's not totally fair because my code is not even as optimized as the current packages, right? What's more complicated in my approach as compared to the traditional random forest, that in each leaf, instead of estimating a sample average, I have to estimate a linear regression. Okay, so basically I have to invert a matrix. Okay, and of course this introduces challenges, but for instance, those simulations that I run, they run in about the 500 simulated in less than an hour. If you want to run this model, right, it goes very fast. Of course, the computational time increases a lot with the dimension of Z, because that's the space that you have to search. Okay, so as of today, so giving you a clear answer, it's more expensive, but the code is not even optimized, right?
So my question is like, for example, if I pick your work to apply for my work, so I want to know like rough estimation. Okay, so how much time it may take? So
the whole thing that I estimated, all the examples that we have been trying run from less than a minute for one full cycle up to an hour. So when we put like 30,000 observations and a Z of 1,000 Zs, it took a little bit over an hour to estimate one model. And when we gave this to like the tree package, I'm a MATLAB coder, sorry, so I run this in MATLAB. So when I use the ensemble function for trees in MATLAB, it ran in a little bit less than an hour for the same case with like optimizing everything. Yeah, so it's
thank you.
It's more complicated.
Final question? Right?
I have a quick question, like when maybe in slide 4, we're subdividing the sample into 2, and
Here?
Yeah, here, and as you said that we'll be taking one group for 2 group for 2 different purpose, and that will make it to approximately Gaussian. But how can you just explain a little bit?
We basically show that the average of trees that run on forest is what we call a generalized U statistic, okay? Which is this ugly thing here where W is a set of the data points, okay? And then there are some results in the U statistic literature that you can decompose the bias of the tree estimation. So T is like the whole tree, right? Into these 2 terms here. Okay. So for this to be Gaussian, this thing here, that's these error terms here, they have to vanish. So basically this vanishes, and then we use well-known results in the U statistics literature to show this is Gaussian. Okay. And that sample selection thing will be such that will make this term here vanish.
All right. Yeah, that makes sense. Thank you.
Because you have, basically, you need to show that you're going to have an expectation of products. And the whole thing that you want to make these 2 things that you are multiplying to be independent. And the way to do this is to say that the first one you estimate with one sample, the second one you estimate with another sample. These 2 samples are independent. Okay? And then you make these things independent. So that's like more or less what's like giving a super simplified approach, but you want to make 2 components independent. And by making that, so this subsampling, and that's the why we need to do it with IID data here. Because with IID data, I can tell you that the pink and the greens, they are independent. Right? The pink sample is independent of the green sample. If it's time series, I cannot do that. So in time series, we have to use a different approach. And the approach in time series that, imagine you have your time series here, right? Instead of dividing in 2, we divide in 3. The pink will be here, and the green will be here. This goes away, and then you switch, you do what we call CrossFit, and you do the same thing and you average the two, but you lose a bunch of observations. So this will work when you have really a large time series. If you have a very short time series, no chance of this working, okay? So that's the intuition behind this thing. And it seems we have been thinking a lot if it's possible to drop, not with this kind of proof tool, right, that you're using use statistics. We have to come up with a different theory to be able to relax that. Honestly, I have no clue how to do it without the subsample.
Thank you.
Thank you very much, Marcelo.
Thank you.